Hello there, my name is Barnabas. I'm going to talk to you about depth estimation in 360 VR videos with a special emphasis on the 3D shape of people. Our goal is to estimate the 3D human shape and the spherical depth maps from monocular 360 VR video to create a semi-synthetic dataset of people to train deep learning neural networks. We'll demonstrate this in the production on real-life challenging sequences, but let's start with an overview of our system first. We capture 3D human shapes and poses to generate a database of spherical depth representation. We call them mannequins. Then we train a deep neural net using transfer learning and use neural inference to turn a 360 video into a depth map. Our approach starts with a multi-view or free viewpoint video capture of people using 36 cameras. And then artificial intelligence pre-processes these images to generate human masks for the 3D reconstructions and to create our mannequins for 3D body shapes. Here's an example video of a production showing how we recorded the original 36 camera views. There you see the output of the AI algorithms for separating the human. And this is what the 36 cameras see. Eventually, we reconstruct all the camera poses and the scene to create the 3D maps for multiple mannequins, which will be used as input to the neural network. To render our 3D mannequins and visualize them in 360 space in front of a virtual camera, we use point-based rendering. We use the same technique to represent depth as a function of the radial distance from the camera in the center, implemented as a pixel shader, with corresponding points shown in white, which are closer to the camera, and black, which are further out. Here you can see a video of how it is done. The rendering pipeline was built in Unity to create the 360 equirectangular representation. We start by the mannequin point clouds. You can see changing the point sizes and variable shapes. We do the same thing for the depth shaders in order to create a depth shaded mannequins placed in 360. We place all these figurines in different poses at different distances and angles and rotation around the camera, creating the final sequences in order to train the neural network. We train the neural networks using transfer learning by using these depth-shaped mannequins in the large and varied dataset. The training set comprises of 227,000 semi-synthetically generated such images. The depth estimation is posed as a deep regression problem using an image-to-image translation from RGB to depth space. We use fine-tuning to train our spherical convolutional neural network to learn the weights from 360 space to depth. We feed the 360 video through this pipeline to generate the corresponding 360 depth representation. On the left, you see the input monoscopic virtual reality image, and then on the right, you'll see the 360 estimated depth. We use a qualitative assessment on challenging real-life videos and automatic generated 6 degrees of freedom representations of the scenes. The first video shows a music clip recording using an old 6 GoPro rig suspended over the stage. You could see the depth map generated overlaid on the original image, showing the performance as well as the instruments around. Our second example is an extreme water slide ride. This is a very difficult situation. You have a head-mounted virtual reality camera, in this case a Samsung Gear, and we turn this recording into a 6 degrees of freedom representation. You could see the visuals above and the generated estimated depth by our network below. Both camera and people move. You see the features are very stable and they could be used for a number of effects. Our third example is from a concert recording where the challenge mostly comes from the lighting conditions. As you could see on top, estimated properly the depth of the people walking by as well as the main performers. This was recorded using an Instapro camera, but we did not use the stereoscopic output from that. Rather, we reconstructed the monoscopic view. That's what you can see here. Thank you very much for your attention. I hope you liked the presentation. You can reach me in the following email.